Okay, let's continue. How can we solve the inclined elements, but we still have the assumptions about neglecting the axial deformation? Okay, so in these example problems, we will neglect the axial deformations of element 2 and element 3. And in this case, we can talk about a general element. Let's say the element is from the node A to node B, and we can always define the local coordinate system. Okay, just like in the previous discussions, usually we will define the local x prime, which is the axial deformation, which is the axial direction of the element. So from the element and from the node A to the node B, we can define the local x prime axis for this element. And if we like to calculate the elongation of this element, okay, remember the x prime direction is always the axial direction. The x prime axis is always the axial direction of this element. So if we like to calculate the elongation of this element, we can simply calculate the ub prime minus ua prime. Okay. If I added the prime to the ua and the ub, so it means that that's the axial displacement, and also the displacement is referred to the local x prime axis. So we can use the nodal displacement ub prime minus the nodal displacement ua prime to calculate the elongation of the element. And also remember, whenever we like to transform if we like to transform the vector components from the global coordinate, if we got the global vector components u, v, and if we like to calculate the vector components in the local x prime, the local y prime system, we can use this formula. Okay, so that's the transformation matrix multiplied by the vector component in the global coordinate system. Then we can get the vector components for the same vector, but they are for the local coordinate system. And the theta, which is the rotation angle from the global x to the local x prime direction. Okay, so that's the very common transformation matrix we use to calculate the transformations between the vector components. So we can get the elongations will be the okay, so that's if we use the nodal displacement in the global coordinate system, if we use the vector components in the global coordinate system, then also we can calculate the elongation of this element. Okay, so So in this case, if we use this formula, then we can calculate the elongation of the element 2 and the elongation for the element 3. For example, if we like to calculate the elongation of the element 2, then it will be the u3 minus u2 times cosine theta plus v3 minus v2 sine theta, and the cosine theta okay. So we can use the nodal coordinates x2, y2, x3, y3 to calculate the cosine theta and the sine theta for this element. Okay, so we have a formula like this one. If we neglect the axial deformations, for the element 2, if we like to neglect the axial deformation for the element 2, then you can say the E2 will be equal to 0. Then we have the U3 minus U2 cosine theta plus V2, V3 minus V2 sine theta equal to 0. Okay, so that's the also that's the kinematic conditions. Okay, so that's the kinematic conditions, and sometimes they are also called the constraint equation. Okay, and usually the constraint equations usually they specify if we have some specified a certain relationship for the elements in the displacement vectors, usually this type of the kinematic conditions they are called the constraint equation. Also, we have the so-called the restraint equation. Usually they are okay. Usually the restraint equations sometimes they are referred to, for example, we know there is a fixed end support at for the joint 1. So we know the U1, V1, also the theta 1, they are equal to zeros. And also for the nodal point 5, the U5, V5, theta 5, they are all equal to zeros. Such kind of the kinematic conditions, sometimes they are called the restraint equations. And the constraint equations, just like the U2 equal to U3, or the equations like this one, it is also the constraint equations. Okay, so for these problems, we got two constraint equations. so there for these example problems, we have two constraints. Equations. E2 equal to 0. E3 equal to 0. Okay. And also we can put them in the matrix form. In these equations, we need U2, V2, U3, and the V3 as variables. Okay, if you like to express E2 equal to 0, then you need to use the U2, V2, U3, V3 as the variable. And for the E3 equal to 0, you need to use the U3, V3, U4, and V4 as variables. Okay, so you can put them together in a matrix which use which is a 2 by 6 matrix. Okay, so you can put you can write down these two you can write these two constraint equations. They are the two constraint equations. And I will give you a homework, and you can practice how can we formulate the constraint equations. If we neglect the axial deformations, how can we formulate the constraint equations? Okay, I think it is only the part 1 of this homework, and later I will give you the part 2 or probably part 3. The part Okay, just like the previous example. However, in the homework problems, I gave you the geometric informations for all these 5 nodal points. So for these structures, there we need to use 5 nodal points and the 4 elements, and we have the E2 equal to 0. E3 equal to 0, and okay, and you just need to formulate the 2 by 6 matrix. Okay, so then you can practice how can we calculate the cosine theta and the sine theta for these 2 elements, and then you can write down the equations. And if you like, also you can use also you can write a formula. If you like, use the global displacement vector. For this example problem, the global displacement vector, it will be a 15 by 1, the 0, 0. It is a 2 by 15. Okay, so since for these two constraint equations, actually the related nodal displacements, there are only six. There are only six nodal displacements. They are related to these two constraint equations. But if you like, you can also use the complete nodal displacement vectors. So for these 5 nodal points, you need 15 degrees of freedom. So for the global displacement vector, it will be a 15 by 1 vector. And we still need to formulate. In the homeworks, you don't need to formulate this one. You just formulate the 2 by 6. But if you like to formulate it in the 2 by 15 matrix, then you just add, for those unrelated nodal displacements, you just add the zeros to represent this equation is not related to these nodal displacements. Okay, so you can formulate both. However, in the homework, you can use the more precise form, which is 2 by 6, which is a 2 by 6 matrix. Okay, after we formulate this matrix, then I need to introduce the Gauss-Jordan elimination method. Okay, I introduced this method in another course. So if you took both courses of this semester, then you have already learned what is the Gauss-Jordan elimination method. And we have the Gaussian elimination method. For the Gaussian elimination method, if we like to solve the simultaneous equations, we have the coefficient matrix A, we have the right-hand side vector B, and if we like to solve the simultaneous equations, then usually the coefficient matrix A and the right-hand side vector B, both of them, they are the known matrix. So we know all elements in matrix A. Also, we know all elements in vector B. And the vector X is called the unknown vectors. So all elements in the unknown vector, they are the unknowns. And we like to solve the set of the simultaneous equations. And the purpose of the solutions, we like to get the unknowns in this vector. Okay, so if we use the Gaussian elimination method, the first step, which is called for the Gaussian elimination method, we have the first step of the solution method. We need to solve the upper triangle matrix. The upper triangle matrix means that we like to get all elements in the lower triangles. We like to make all elements in the lower triangle equal to 0. Okay, that's the four-wall elimination method. And that's the Gaussian elimination method. But if we use the Gauss-Jordan elimination method, then in the four-wall eliminations, in the Gauss-Jordan elimination method, we will make it both both lower triangle and the upper triangle, all elements equal to 0. And all the diagonal elements, they must be equal to 1. So that's the unit matrix. Okay, so if we use the Gauss-Jordan elimination method, the coefficient matrix, the original coefficient matrix, we need to change their elements. And the purpose of the Gauss-Jordan elimination method, we will make all elements in the lower triangle equal to zeros, and all elements in the upper triangle, we will like to make them equal to zeros. And all the diagonal elements, they need to be equal to 1s. Okay, that's the Gauss-Jordan elimination method. So after you do the forward elimination, since the coefficient matrix has already modified to the unit matrix, then the unknown vector x will be equal to the right hand side vector for that's the x is equal to b double prime. The x is should be equal to this. But if we use the Gaussian elimination method, the elements in the x vector, we need to use the backward substitution. We need to solve the unknowns from the last equations, the second last equation. We need to go back equation by equation and to solve the unknowns. So the Gauss-Jordan elimination method, which is different from the Gaussian elimination method. However, the solution procedure, they are similar. So, okay, I think I will take a break here and continue the discussions in the next hour.